Okay, fine. We'll start the session. Just someone please confirm that actually the screen is visible. Anyone please? Is my screen and visible? I'm just expecting an yes or no. It's okay.
Yes, yes, sir. Yes.
Thank you. Thank you so much. Okay. Okay.
Thanks.
So let us start the week 7. Okay. Week 7 of the control engineering. Okay. Basically, the week 7 is we have to deal with the compensator and controllers. Okay. And we have to solve lots of questions. Okay. So how these controllers and these compensators will be very helpful in designing the system. Okay, how can you get the stability of the system if time permits? Okay, I will also show you that actually in MATLAB how can you design the compensator. Okay, uh, so let us quickly just start with the basic thing. Okay, so you know that basically this is a system. Okay, and some please everyone please mute yourself. This is the input. Okay, and this is the feedback HFS. It can be negative feedback, it can be a positive feedback. Okay, mostly control system and low pass filter, so basically you deal with the negative feedback system to achieve the system stability. So in this plant transfer function, let us assume that this is a system where you have some input and output. Okay, let's say at some point of time your disturbance is coming somewhere in the system. Okay, then how in that disturbance actually your system becomes unstable. So how to achieve the system stability by using some external block. Okay, generally we are using some external block in the form of a controllers. Okay, so so in control system, generally in this course, actually we'll go to define three types of uh, controllers. Okay, so basic you know that a proportional controller, it is denoted by its gain KP. Okay, similarly, another type of controller is integral controller. It is denoted by a constant Ki. Okay. Similarly, another one is derivative controller. It is denoted by its coefficient Kd. Now, what we are going to do, we just try to understand you, because if you already gone through the course, then you have some idea about that where you can use the proportional controller, where you are using the integral controller and derivative controller. But in some systems actually you can use both, combination of all the two or combination of all the three. So another two types, so by combining I can get a PI controller. Okay, you can say this is one block diagram where the output is, let's say, control this gain in GCS. I'm saying the gain of the compensator is GCS, its output, and it is input of the system. The input of the system is basically to a compensator is called the error signal. Okay, basically it is what is doing. Basically, I am just taking a PI controller. Just give an example. It can be a PD controller, it can be a PID controller. It is normally it can be only integral controller, only a derivative controller. So that block that I'm showing, the gain is GCS, it can be anything, any combination you can check based on the system design, what you're going to deal with, where is the plant, which type of error you are encountering in the system, how much fast accuracy you want in the system.
Sir, can you call this PI controller as a proportional plus derivative filter?
PI controller can be proportional plus derivative filter. No, it's a proportional plus integral filter, you can say, not a proportional plus derivative. PI means this is proportional plus
Yes, yes,
integral.
proportional plus integral.
Yeah, I'll
Yes,
tell
yes.
you all these things, that how can it can behave as a low pass filter, it can be behave as a high pass filter, combination of it can be behave as a notch filter, band pass filter. So all this
Okay, sir.
combination is possible. I'll tell you, I'll go through some questions numerical based on that. So you just try to understand that why we are using a compensator. Okay, so in MATLAB how we are going to deal with this. Okay, so generally because when you are going to design a control system, the main focus is that you have to design the system dynamics. Okay, so what do you mean by the system dynamics? You have to model the plant according to the input, output, and the disturbance, noise, okay, whatever. Then after doing some small signal modeling or a large signal modeling based on which one is uh, required for your system, then you are going to come up with a compensator that can minimize the error, and we can properly track our output whatever the reference we're giving. Let's say in the system, let's say I'm just giving a practical example. Let's say you are doing a voltage control. Okay, let's say you have a buck converter. As you, someone who is very familiar with the power electronics, they know that what is a buck converter, boost converter. So in this type of way, okay, you can take any, let's say a electric vehicle charger. I'm giving a practical example. So let's say you want to control the output voltage. Okay, let's say my output voltage is 400 volt. Okay, so what is happening during the charging time, what will happen, the charging profile is based on the battery. There is a battery which is charging in CC mode and sometimes in CB mode. CC means constant current mode, and then it is going to constant voltage mode. So what is happening initially, the current is constant, after that the voltage is constant. So what, how your battery is going to behave, okay, during that process of charging, because any battery, you take a lithium ion battery, you have to go through all this battery means constant voltage and constant current profile, because the battery cannot be charged only with the constant voltage. So you have to follow, sometimes when the constant current mode, your battery voltage suddenly increases from, let's say, 10% to 90%. So like that, in that wide voltage range, let's say you have a 12 volt battery. Okay, nominal volt 12 volt what we are using in our PC. Okay, somewhere 24 volt battery or 48 volt battery, that is using electric vehicle two-wheeler battery. Okay, so let's say for a 48 volt battery, let's the upper limit of the 48 volt, let's say it can be go to 54 volt, and the lower limit of 48 volt is go to 36 volt. Let's say I'm assuming for this wide voltage range, when your battery will be charging, then you want always the nominal voltage should be maintained at 48 volt. So but your battery voltage is swinging from 36 to 44 54 volt. So in that case you require a, your error will be there, because we are providing a reference command of 48 volt. We are giving that it should be track 48 volt only. Reference we are providing 48, but whenever you are achieving a 54 volt, when the voltage is constant 54, then at that time the error will be maximum. Okay, so in that case you have to come up with a compensator like a PI controller or a PID controller, such that the error will be minimized. The PI controller is just a controller that minimizes the error. Okay, and it achieves a steady state stability, and it makes the steady state error zero with a very accurate bandwidth. Okay, so we don't want that our systems is slow, so the bandwidth should be of the system should be properly maintained according to the frequency what you are going to operate the system. So this is basically a practical application that where the PI controller is used. Similarly, sometimes proportional plus derivative controller is used some applications where you are to deal with the transient response analysis. Okay, we want fast accuracy system, means accurate means we don't allow much overdamped, or we don't allow much underdamped system. We want our peak overshoot should be very very less. So in that case, we are going for a proportional plus derivative controller. But for a personal plus integral controller, where you have to minimize the error. Error is basically the steady state error. So many in application electrical engineering people are always try to minimize the error. That's why they are going for a generally basically a PI controller. Okay, because the PI controller is always deal with the DC systems. Okay, so if your system having a AC, you have to convert into a DC, then you can use a PI controller. But if you directly you can use, suppose your input is AC but you want to track a sinusoidal reference, then you can use another type of this one is it is not here in this course. This is called PR controller. Okay, this is a proportional plus resonant controller. Okay, so in advance, if you go for another type of controller, this PR controller is available. So that I'm not going in detail that how inside all these things will be there. So based on our course, we have to just stick to some of the questions related to PI controller, PID controller. Okay, how they are dealing with the steady state error. Okay, so let us I'm just giving a question number one in front of you. There are four options are there: a derivative control. Okay, and what is the four options? Which one is correct? Can anybody guess?
It reduces overshoot.
Yeah, you are right. Absolutely, it reduces the overshoot. Okay, so try to understand that why the first option is not correct. The first option is not correct because he's giving in that a derivative controller is there. What is the mean derivative means? Derivative is means you are adding a pole into any system. Okay, that can be a pole at origin. Okay, sorry, you are adding a zero. Okay, I'm sorry, you are adding a zero. That zero in the system, that zero can be at the origin. Okay, it can be of some, let's say I'm writing numerator by denominator. Okay, some transfer function g of s. Okay, so whenever you are adding a derivative controller, you have to add a compensator. You are making, so that compensator you are adding some pole. It can, sorry, some zero. If this zero can be at origin, if it is origin, then it will be only s. So what will happen? This if you write the total transfer function, now GCS into G of S. Okay, this is the total transfer function including the plant and the compensator. So what will happen? This S will be multiplied in numerator and denominator. If you are adding a zero at the origin, suppose you are adding a finite zero at somewhere, not at origin, then the transfer function becomes GCS into G of S is something like S plus, I'm taking a constant. It constant can be any value 1 plus 2. Okay, anything numerator by denominator. So you are adding a finite zero. Okay, so what will happen if you add a derivative term? Okay, so that basically what will happen, it reduces the overshoot of the system. It reduces the overshoot of the system. Let's say for a unit step transfer function, and for a step input, you know that it's very, your step response will be very like that. Okay, okay, so what will happen if in this g of s, if you add gcs any value, this combination you can take and add, you are adding a derivative control, then what will happen, the here this is the reference value. Okay, so its overshoot is suddenly it is going to decrease. Okay, this overshoot is going to reduce this value, whatever this value is here now. Okay, this value is going to reduce. Okay, and you can achieve the peak value at a faster response. The rise time that will be reduces. Okay, because bandwidth of the system is increases. So you know that the rise time is inversely proportional to the bandwidth. Okay, so in this case, if you achieve a faster response, the rise time you have to reduce, because time has to reduce, then only you can achieve speed. Okay, bandwidth is nothing but your speed. Okay, that's why you have achieved a bigger bandwidth of the system. So how can you verify that? There are lots of way you can verify that. So I'm just giving an example. Let's say g of s is something s, let's say 1 divided by s plus 1. This is a simple transfer function I'm giving to you. If I'm adding a compensator of one finite zero, let's say I'm adding s plus 2 divided this is s plus 2 only, this is the derivative term. Okay, if you add it to the system, then what will happen? Let me write here. Then what will happen? Your plant transfer function become gcs into g of s is something like that, s plus 2 divided by s plus 1. This is the whole transfer function now. If you do the Bode plot of the system, okay, so initially what will happen, one pole will be here, let's say this is up to some point it is a constant, then you are encountering a pole at this point 1, then what will happen, it will be decay at minus 20 decibel per decade. Then what will happen at the point 2, again you have to add a 0, so that minus 20 and plus 20 becomes cancelled, the slope will be again 0 decibel per decade. So you can clearly see that how this transfer function will happen. So initially if you draw the transfer function 1 by s plus 1, this 1 by s plus 1 is simple, you can say like that, suppose my initial slope is 0, then if you're adding a pole, then this transfer function is something like that, means Bode plot. So you can see your bandwidth is now limited to this region, but here what will happen, your bandwidth is limited to up to infinity. Okay, this bandwidth, not I'm saying infinity, it can be, it depends on other factor like system gain and everything, but you can see it clearly from figure 1 to figure 2. If you go, then by adding this derivative control, you can see that the bandwidth is increases. Okay, so if bandwidth is increases, the rise time it decreases, it reduces the peak overshoot. So that's why the option should be the right answer. And you can see it, steady state error, the first thing that whenever error term is coming into picture, you always think in your mind that okay, there is something like a pi controller or proportional plus integral controller will be there, okay, rather than
Sir,
derivative.
I have one doubt, sir.
Yes, sure.
If it is a second order system, sir, and if proportional plus derivative filter is added,
Yeah.
then what? Suppose proportional plus derivative filter is 1 plus ks,
Okay.
and if this filter is introduced in the second order system, what will be the value of k, sir?
You can find out there is typically some whatever you are pointing out. I will take one question related to that. I'll take a second order system. I'll add some pi controller. Okay, into that we'll find out the k value. Okay, you understand what I'm telling?
Yes,
You are telling that you have a second order system. You're adding some pi controller.
proportional plus derivative filter,
Yeah, you can.
PD.
Okay, you can add some PD controller. Okay, then you can find out the k value
Yes,
based
sir.
on some. Okay, we'll do some question related to that. So you understand this question how it will
Yes, sir.
reduces overshoot, and the steady
Yes.
state term is basically a proportional plus integral term. Okay. Next question. So you can see something related to your question. I have just taken one question related to that. Okay. So now you can see here. Try to read the question and find the derivative time. This is a similar type of question what you're raising. You have a second order system plant g of s. Okay, this is second order plant system. You are adding a compensator. Okay, like that. It is in time domain. It is given to you 20 into e of t plus td into derivative. So you can clearly understand that if something is in this format and derivative is there, it will be some kp plus kd. Okay, like that term. So the first term, if you take the Laplace transformation of this theta cs, then you will get 20 e of s, okay, plus td into s times of e of s. Okay, now you can clearly see that the first term is related to kp and the second term is related to your derivative. I'm not writing here, just to write down derivative term. Okay, s into td. What is this td? This td is nothing but kp by kd. How it comes, I will show you now. Okay, so this is the derivative term. Okay, so this is a theta cs. Now in this plant transfer function, which is second order system, and for that you are taking a unity feedback system and you are adding a pd controller. Okay, so first question is asking that find the derivative time required to make the closed loop damping ratio equal to unity. So what is that Derivative time required means you have to find out this TD value. Okay, so first do this and we'll go through find out the uh, from if you find out TD, then from TD we can find out KD value gain. Okay, so do this question, try once. You first note down this question because I'll go to the next slide. Okay,
Yes, noted down, sir.
okay, let me quickly go to solve this question. Just 1 second. Charger. Okay, so my question was that we have already find out the transfer function. So again, what do you need to do? Find out the open loop transfer function. Open loop transfer function is nothing but g of s into theta cs. Okay, just to multiply these two. So what was the previous value here? Can go back one step. You can see this 40 divided by 10s square plus 80s plus 800. Okay, I'm just writing here directly. 40 divided
40 divided by 10s
s
square
square plus 80s
plus
plus
80s
800.
plus 800.
Okay, now in this you have to multiply theta cs. Theta cs in the previous slide, what was the
20.
value?
Yes, I am telling, sir.
Okay, okay, right.
20
20 into
into
1
bracket E of t.
1 plus s into td, right?
Yes.
So you already know that for this system how to find out the closed loop system transfer function, because I told you for a unity feedback system, so how to write the directly without doing anything. So write down the transfer function, closed loop transfer function. This is the open loop transfer function here. This is the open loop transfer function. You have to find out the closed loop transfer function. So what you do, you write down first numerator. So 40 into 20 is mostly 800. Plus you can simplify it a little bit. Okay. Now it will be how much? 10s square plus 80s plus 800. So whatever this numerator term, you just simply add in the denominator. So it will be 40 into 20 plus 20 s into td. Simplify it quickly. Okay. So after you just simplify it, closed loop transfer function, that will be 40 into 20 plus 20 std, because we have to only deal with the denominator part. So numerator part we're just keeping like that. It doesn't have any problem. So one second, just turn the charger in the laptop. Okay.
10s square
10 square
plus
plus
in
80s
bracket 80 plus 800 TD.
80 plus 800 800 s into td, right?
Yes, I have taken yes outside above from
Okay,
this.
you can take outside, no problem. I'll just write down s outside. Okay.
plus 1600.
1600.
Yes, sir.
8 800 plus 800 is 1600, right?
Yes.
So now he's going the question, if you go a little bit here is saying that the damping ratio is unity. Okay, so in this case what you need to do, with that for standard second order system you have to compare. Okay, omega n square divided by s square plus 2 zeta omega n s plus omega n square. This is a standard second order system. We just now, this is a closed loop system, we just compare the denominator part of both the things. So what is happening, people really doing mistake. What they are doing mistake, they are directly taking omega n square equal to 1600. That is wrong. Okay, don't do this, because here the coefficient is 10 and here the coefficient is 1, so you have to make the coefficient equal to 1. So you divide 10 everywhere. Okay, if you divide 10 everywhere, then I'm just rewriting it. This, it becomes 8, this becomes 80, and this becomes 160. Just I have divided 10 everywhere in the okay, in the denominator. Then what will happen, your omega n square is now becomes 160. Okay, so your omega n square is 160. So now if you find out omega n, how much, root over of 160, root over of 160 is how much, calculator. So 12.65. Okay, so the omega n is coming 12.65. Next, what you do, you compare your 2 zeta into omega n equal to 8 plus 80 into tt. Okay, so here zeta equal to 1 is given, damping ratio 1, omega n you find out 12.65. Then from here you find out your td. Okay, once you find out td, what is the value of td? Okay, you solve this, because in the question he is asking us to find out the derivative time required. Derivative time is nothing but td. So
0.216.
0.216. Once you get td, if he is asking to find out, okay, if in further question if he is asking to find out the system gain kp and kd value, then you use this relation td equal to kp by kd. Okay, sorry, td equal to kd by kp, because kp is the reference. Okay, so from here you can compare. Okay, so in this question 20 into e of s, so 20, if you take the e of s outside because it's a error term, then 20 plus std. Okay, so this 20 is nothing but your kp value, and this td you already find out. Okay, so td is nothing but your kd by kp, so kp you already know 20, so from there you can find out the derivative constant. Okay, or the gain of the derivative. Okay, so in that way you can find out. But to any second order system we're going to solve, there should be some constant. Like here in this question he is giving to you that actually to maintain the closed loop system stable you require the damping ratio unity. Okay, for it, so like that, something or something related to like suppose you am asking the peak overshoot should be 90%, so something you have to give, and then only you can find out the other parameter from by giving known parameter. Okay, so like that you can solve some question. I have lots of questions. Okay, it's not only one question. Let me do another question. You understand this question? It's a little bit simple question. Let us come to this question number 2. So you can see in the questions, question number 2, right, first read the question. What is the question? If there is a plant is given whose transfer function is given g of s, okay, and a controller is given which is a gc of s, okay, and For a unit step input,
So,
the
sir,
input
in last question, how did you get 1 plus STD?
1 plus, sorry,
STD. 20 into 1 plus STD.
you can simplify this theta ct na. I already simplified this. Is here you can take S common because that is the compensator. Compensator, why I told you in the compensator, I told in any compensator the input is the error signal. Okay, 20, if you do the Laplace domain of this theta ct which is given in time domain, then you can come across this step. Okay, this step is clear because I just taken the Laplace transformation. Now what I did, I taken the E of S common. If I take the E of S is common, then 20 plus STD. Okay, okay, because this E of S I taken common here, this E of S outside. So now any compensator, this is GCS. Okay, here the input is E of S, you'll get some output. Okay, okay, so now GCS is something combination of either a proportional controller or a combination of proportional plus derivative, proportional plus integral. So here it is clearly that in the question you can see this derivative term is there, d by dt term is there. So that's why I'm just, this td is the derivative uh, time constant. So this td can be come based on kd by kp. Okay, this relationship actually if you go through the lectures you can understand this betterly. Okay. Uh, if you understand it, next let me move to the next question. So please try to unmute yourself. Some buzzing sound is coming. Please everyone unmute. Yeah, thank you. Now come to the question number two. In the question number two, we have a plant. I told you GFS. I have a compensator GCS, and a unit step input is given. So he is saying that you have to find out which compensator will be fit in the place of GCS to give a minimum steady state error. Okay, to give a minimum steady state error, just try to understand. If you have to deal with any question which is related to minimum steady state error, then whatever the compensator, that compensator is related to your proportional plus integrated term or only integrated term. Proportional means what? What proportional term you are adding because whatever the error is coming, because if someone please unmute yourself. Okay, so proportional term is why there is a proportional term, because this is a compensator. Try to understand GCS. Okay, so here the error is coming. This error is nothing but your input minus the feedback term. The summing block is there, this feedback is coming from the output. This is the error signal. Okay, that we discussed lots of times. Okay, so this error signal is very small value. Okay, sometimes what will happen, the compensator will not able to identify what is the error value. Then what is this proportional? We are adding a proportional term only to magnify that error. Okay, just to scaled up. Let's say this error is coming 0.001. Then I am just adding a value of kp multiply with 10, so I can get up to 0.01, or you can multiply 100, you can get 1000, you can get 1. So like that, because any small error we need to identify. Okay, then only we can able to minimize it. So that is the role of the proportional controller. It has nothing role. Okay, the other two terms, like derivative and integral term, it will be help you to minimize the error. So derivative term will be reduces your overshoot and it will have a better transient response, and the integral controller is used to reduce the steady state error. Okay, it doesn't deal with the transient response. So in this question, the question is telling you that you have a minimum steady state error. Minimum steady state error means you have a integral control action is there. So you have to find out which one out of these four options, which one having a minimum steady state error if you put the compensator. Okay, you understand the question? Then how can you deal with this question in very less time? Because otherwise what you will do, you have to take the plan transfer function g of s is 1 by s square plus 2s plus 1. Okay, Then this GCS you have to multiply. The first option is s plus 1 divided by s plus 2. Okay, then you have to find out, take the limit s tends to 0, s into e of s. This is the steady state error value. Okay, e of s is, okay, you do one by one and check which one having a less steady state error. Okay, but if you're a little bit smart, okay, if you know the answers that I already told you from the last class, the two things I told you, one is type, other one is given input. When type and input means there are three types of input in our control system. Okay, one is a unit step input, another one is ramp input, another one is parabolic input. Okay, so this is p of t. So u of t is nothing but t to the power 0 u of t. I told you it can be written like that. R of t is t to the power 1 u of t, and parabolic input is t square by 2 u of t. If you attend my all my lectures, then you can easily catch up this. Okay, then type is defined by the number of poles at origin. Let's say you have a type 0 system, and it can be type 1 system, can be type 2 system. So remember that when equal to type equal to 0, so when your type equal to your input, okay, whenever your type that is equal to your input, at that condition, if it is the first case I'm taking 0 and 0, then in that case what will happen, one steady state error will be exist, and that steady state is nothing but 1 plus kp is called a positional error constant. In the second case, if type equal to 1 and input equal to 1, in that case some steady state error will be exist, and that steady state equal to a divided by k into v. Kv is the position or velocity error constant, you can say. For parabolic input, if 2 equal to 2, in this condition the steady state error equal to a divided by acceleration error constant. Okay, if apart from all these, if type is greater than input, okay, then your steady state error equal to 0, and your type is less than input, then the steady state error is infinity. So remember all these 5 points. Okay, so based on the 5 points, so now you can clearly see, if I am just putting the first option, if you push the first option s plus 1 divided by s plus 2, then you can see that what is the type of the total system, GCS into G of S. This is a Planck transfer function.
Sir, when the type is less than input, what is the steady state error?
This is infinity.
Okay.
Steady state error is infinity. Let I'm giving an example. Let's say your type means you have only type is defined by the poles at origin. Let me give an example. In this question, GCS into G of S, this is open loop transfer function. So tell me how many poles at origin is there?
There is no pole at origin.
So there is no pole at origin means your type will be 0, right? Your type will be 0 because there is no pole at origin. Now suppose I am adding a ramp input. I am adding a ramp input. If type is 0 and you are adding a ramp input, then you can see ramp input means t to the power 1. Okay, so here now type is 0, so now you are comparing 0 with 1, so which is greater than, type or input? So which condition is satisfying? Type is less than input. As type is less than input, your steady state error by default is infinity. Okay, don't do that.
Type is less than input.
Yeah, type is less than input, so steady state error is infinity. But here in this question, what is there in the question? He is giving a unity step input. Unity step input means t to the power 0. Okay, t to the power 0 means uh, 0. Okay, and your type is also 0. So now 0 is matching with 0. If 0 is matching with 0, in that case you will get some steady state error, and that steady state error is in this formula, a divided by 1 plus kp. Kp is not kp, kv and k all are called DC gains. Okay, kp, kb and all are called the DC gains in my term. But if you understand what is kp, kp is called the positional error constant, kv is called the velocity error constant, and k is called the acceleration error constant. Okay, all are DC gains. DC gains means at zero frequency what is the value. So now you try to understand that if you put s plus 1 divided s plus 2, then find out that DC gain. For the decision, everywhere just put s equal to 0. If you put s equal to 0, then it will only 1 by 2 will be
0.5.
there. Okay, 0.5. So if you put 0.5 in place of kp, so it will be a equal to 1, because a is nothing but the coefficient of this unity step input. Okay, a, here you can add a value. Okay, so let's say it is not a unit step, it can be 5 u of t. So in that case, your a equal to 5. In that, assume that like that. So now here a unity step input is given, a equal to 1. So a equal to 1, I am putting a equal to 1 and kp equal to 0.5. So now you simplify it and find out the steady state error. Okay. So for the first case you find out, for the second case you find out, for the third case you find out, and for the fourth case. Fourth case I am clearly seeing that it's a type equal to, if you add this system into, you will get a type 1 system. If you type 1 system unity step input, here the steady state error will be 0. So I can understand that for the fourth question the error will be 0, and you find out for the remaining 3 what is the steady state error, and you just to make a conclusion that which is having a minimum steady state error out of these 4 options. Okay, so I think this is a pretty clear question, because generally basically compensator and controller basically used to minimize the error. Okay, so if you understand clearly time response analysis, steady state error, the concept of type and input, okay, and what is position error constant, what is velocity error constant, what is acceleration error constant, then you can easily find out by just you're adding a compensator GCS into your plant, multiply that, you'll get open transfer function, find out the closed loop system stability, any methods, you have RH criterion, you have a root locus method, so just figure out that what is the value what the question is asking to you. Okay, so let me move to the question number 3.
Or we can also use this formula, sir, na? Steady state error. It will
Yeah,
take
you
time.
can directly, it will take time. Okay, basically if you attending any like engineering solutions exam where you have conventional papers are there, then you have to go longer methods, you have to go in details everything. But as mostly people are preparing for the numericals, so time is important rather than the methods you are adopting. So you have to be smart. Okay, at the time people are doing 5 questions, you can able to solve at least 10 questions. Okay, so let me come back to question number 3. I'm a little bit going slow today. Okay, so you try to understand this question, read once and figure out, because this is simple question. I think everyone can answer this question. In my point of view, I have already discussed a lot of background related to zero steady state error. Read the question, try to understand. Always in your mind what you do, you have to figure out. This is my plant GeoPace, and this is a controller is given to you GCS, but which only a kp value equal to 1. So this is the plant. Okay, this is having a kp plus ki, so kp plus ki by s, this is the plant transfer function is given. This is your GCS. Okay, this is your input and this is your output. So what is happening when feedback is coming from the input and output, there is a summing block. Okay, it is getting subtracted, this error is coming e of s. Okay, here we want to minimize this e of s so that our reference should exactly match with the feedback. That is the concept in every control action. Okay, if you're doing a closed loop control, always this is the necessity that you have to minimize this error EFS. So that for that, to minimizing this error EFS, we are using a compensator which having a plant transfer function. Now in this question, this plant transfer function kp value is given to you 1, is asking us to find out what is the value of ki. Okay, such that okay you have achieved a zero steady state error, and you can clearly see that a step change in the reference input means your reference input is a step signal. Okay, solve this question and tell me the answer ki. What is the value of ki? Just to solve steady state error question, figure out the type, figure out the input and tell me the answer. What is the type of the system? If you multiply, type means always now GC of S into G of S. what is the type of this total open loop transfer function? What is the transfer function? 2 divided by s into s plus 3. There is a 1 divided
Type
by
3 system.
kp plus,
Type 3 system, sir.
sorry,
Or sorry, type 0 system, sir.
I'm just finding out type. Okay, let me find out. Multiply this 2. Okay, this will be how much? Kp into s plus ki divided by s. So you can see that how many poles at origin are there? 2 poles at origin. So type of the system is 2.
There are two poles.
Yeah, there are 2 poles in the system. So it's a type 2 system. Now you can understand type 2.
Type 2 system.
Find out input. What is the value of input? The input is given that it is a step input. So t to the power 0 u of t. So here is 0 is coming, here is 2 is coming. So type is greater than 2. Type is greater than your input. Okay. Once type is greater than your input, then what is the steady state error?
Zero.
0. So steady state error is 0. So what you understand from this question, that you can see here, we are solving this question, we are finding out the steady state error, but the steady state error only depends on your type and input. It doesn't depend upon the gain value, because you can see your kp and ki is always in the numerator term, but we don't have any care about whether they are it is not coming into your type and input. Okay, so always you are getting a steady state error 0 for all the values of ki. Doesn't matter whatever the value of ki and kp you will put, it doesn't matter for this system. For all the values of ki, okay, you will get a 0 steady state error for this system, because your type always greater than input. That's why you always get a 0 steady state error for all the values of ki. So answer will be D.
So answer is 0, sir. Or actually last answer.
Yeah, you can put any values of ki, it doesn't matter. See,
Yes, yes.
if you put 2, 3, 5, whatever, whether your type and input will change by adding these kpki values? No. So type doesn't depend. So that's when if you put any value of ki, will satisfy this equation. So that's why the answer will be all the values of ki. Try to understand that how you're approaching, because approaching the question is little bit tricky. You don't waste your time to find out, yeah, kpk depends on some value, or some people, what they will do, they will try and hit and method. They will take ki value initial first option 0, then they will take 2 by 3, they will take 1, and they will find out the steady state error. So basically just observe that if you doing all these methods in the examination, how much time it will take. So there's a different approach to solve the questions. Okay, so let me move another questions. Okay, let's go question number 4. What is this question? Yeah, so this is a question I have. This question I have taken from the previous year, I think, NPTEL. So you can see here what is the question is asking us. If a proportional controller, in place of GCS, GCS is nothing but only a proportional controller. Okay, so if you use a proportional controller having a gain of kp, find the value of the controller gain kp. We have to find out what is the value of kp to achieve a steady state error of 0.25 for a ramp input. So how many of you understand the question, and how many of you try to solve this question in less than 30 seconds?
No, I understand the question, but I will not solve less than 3 seconds.
Not 3 seconds, I'm just giving 30 seconds. If you understand the question, if you apply the previous concept to what you learned, then you can able to solve the question in less than 30 seconds. So try to understand the question. You understand the question clearly, right? Now your GCS into G of S, I am writing, otherwise I can directly solve here in my mind. So 4 into Kp, okay, divided by S square plus 2S. This is my total open loop transfer function. Now in the open loop transfer function, what is the type of the system? Can anybody tell me? What is the type of the system? One. Type, clearly it is see that one pole it exists at origin, so type is 1. If type is 1 and you have a steady state error, definitely it should be a ramp input. You understand? So in the question he is giving us it is a ramp input. It has to give because type is 1, type equal to input, then only some steady state error will be exist. Okay, you can go come back to the last slide. You can see here, if type is equal to input, in this second case you can see here, okay, 1 matches in 1 has to be matched with 1, then there is a steady state error, that is A by kV. Okay, kV is the velocity error constant. So now if I come to here, then the steady state error equal to, for a type 1 system, is A divided by kV. Okay, A equal to 1 because ramp input is unit ramp input. Unit ramp input means A equal to 1. You have to just find out kV because steady state error is given to you 1 by 4. 0.25 is 1 by 4. So 1 by 4 equal to 1 by kV. It means kV equal to 4. Okay. If kV equal to 4, then what is kV now? kV, I told you, this just the DC gain. Okay. So what is the transfer function? 4 kp divided by, I am just writing here, 4 into kp divided by s into s plus 2. Okay, so whenever you're finding out the DC gain, don't consider the pole at origin. So remove the pole at origin. Now, in your mind you have to remove. Okay, remove the pole at origin. Put s equal to 0. If you put s equal to 0, then it will becomes 4 into kp divided by 2. It means 2 into kp. So 2 into kp is nothing but a DC gain, and that DC gain is nothing but a kV. So 2 into kp is now becomes here 4. So kp equal to 2. Okay. So like that you have to find out what is the value of kp. If you understand this question clearly, let us move to the next question. I just want to do some question related to compensator. Okay. Okay, coming back to the next question. This is the question is over. Okay, this 5 and 6 are interrelated. Okay. Now in place of kp, if an integral controller is used, ki by s, okay, in the forward path, okay, then the steady state error to a unit ramp input, how much? Okay, I think this question number 5 you can able to solve now. Okay, question number 5, forget about question number 4 because you already solved this question. Okay, this is solved. Question number 5, in place of gc, now the gc is replaced by a only integral term. Okay, so this gcs is this one. So find the steady state error to a unity ramp input. If this will be, just assume that if this is, let's put ki by s. If it will be put ki by s, then now tell me what is the type of the system. Here is one s is coming out. Okay, this s into s plus 2, and here is one s. So total now 2 poles at origin. So type equal to 2, and type equal to 2 and is giving ramp input. So input is now ramp, it means equal to 1. Okay, so type is greater than input, so steady state error equal to 0. So answer for the question is 0. You understand question number 5?
Yes, sir.
Okay, if you understand question number 5, then this is I think question number 5 and question number 6 are database question. Yeah, I think it can solve it. If a 0 is added, okay, to GCS at S equal to -2, okay, then GCS equal to 1. So what is it telling us to now? Here your G of S, okay, and here is GCS equal to 1. He is giving this value is 1, so we don't care about that. But in G of S we are adding a 0 at S equal to -2. So previously what is the value of your plan transfer function? 4 divided by S square plus 2S. So I'm just writing here G 4 divided by S square plus 2S means S into S plus 2. This is your plan transfer function earlier. Now in this transfer function you are adding this value at S equal to -2. You are adding a 0. So 0 means you are adding S plus 2. Now this is the overall transfer function. This is your open loop transfer function. So now in this open loop transfer function, what is the velocity error constant he is asking? Here you can see that the type equal to 1, input also equal to 1. Why the input equal to 1? Because he is asking the velocity error constant. So it should be a ramp input, okay? And A divided by kV, okay, you need to find out. Do it. What is the value answer? What is the DC gain of the system? Forget about this S. What is the DC gain? S plus 2 and S plus 2 get cancelled. So the DC gain is 4. So it will be 1 divided by 4. Okay. This is your steady state error. What is the value of kV? kV is nothing but only 4. If you compare here, we'll get kV equal to. Please mute everyone. Okay. So this is a little bit easier question. Okay. Let me I just want to solve because this part you are, and I understand that you will able to solve it. Okay, let me move related to lots of slides in my question like that you can solve by yourself. Okay, and doubt you can, these are very simple easy questions. Okay, they like to solve the characteristic equation, find out the characteristic equation, find out the numerator terms and denominator terms. Okay, by solving the characteristic equation I just compare. Okay, uh, okay, let me deal with a new chapter. That's a new chapter. This is just a compensator thing. Okay, because you know that actually we have to deal with the types of filters now. Which filter, whether a PI controller is a which type of filter, okay, PD controller is which type of filter. Okay, so basically to solve this type of question, compensator means there are two types of compensator basically is coming. One is lag compensator, another one is lead compensator. Okay, so lag compensator, try to understand what is a lag compensator. If you are having input is sinusoidal, okay, let's say you are assuming that you are giving a sinusoidal input at the input. If you get an output, let's say some signal I'm giving, and this is sine wave, and the output what you are getting its phase which is leading the input. Okay, this is the output. This just 0 is, now you can see it is leading the value. Okay, so in this case it is called a lead compensator. Okay, so if it is lagging, let me quickly draw for the lagging compensator first. If it lagging, it will be like that. So if this theta is lagging, your output is lagging from input, then this is called a lag compensator. And if your output is leading the input, you will get a lead compensator. It depends on theta. Always you have to check the theta value. So you have to, what you do, you have a plant transfer function. Okay, this is a combination of the plant plus the compensator, like the open loop transfer function. What you need to do, you have to find out the angle of the overall open loop transfer function. Then you have to check whether at that particular point the angle is leading the input or the angle is lagging the input. Okay, okay, at a particular frequency you can check it and you can observe that. Then you can conclude that it is a lag compensator or the lead compensator. Okay, otherwise what you do, then let me give an example. Tell me, this lag compensator is a low pass filter or a high pass filter, or a lead compensator is a low pass filter or high pass filter. You have two options: high pass filter or low pass filter. See how when I was reading, how I remembered this. Lag is 3 term, it should be low pass filter. Lead is a 4 term, it is a high pass filter, because high is having 4 letters. Okay, so like that. But actually, how this thing will be, how can you realize? By doing simply a Bode plot. Quickly you can do. Lag compensator means, I'm just going to next slide. Okay, lag compensator means your angle has to be lag. Okay, remember, angle has to be lag means you have a always at pole at origin and a zero at the right left side. Okay, which one is very close? A pole should be always close to origin. If you quickly draw the Bode plot of the system, then how it will be? Let's say I have initial gain of k, then at what, then you are encountering a pole. If you're encountering a pole means you will be minus 20 decibel per decade. Then what will happen? You are encountering a zero. Encountering a zero means you'll again going to the same slope. At which slope you're falling? The same slope. And if you come back, it is minus 20. If you add a 20, it will be 0 decibel. So you can see clearly that it is a low pass filter which allows only the low frequency component and it's blocking the high frequency component. Similarly, if you have a lead compensator, your zero should be very close to a pole. Okay, then what will happen if you do the Bode plot of the system? You can clearly see that you have a zero initially. Zero means what will happen? You are, let's say you are starting from zero. Okay, then what will happen? You are plus 20 decibel per decade. Okay, this is plus 20 decibel per decade. Then again you have a
Sir,
pole. Then you
sir,
have to come.
in this previous case, sir, pole is having minus 20 dB and zero is again plus 20, na?
No. You are just unmute yourself and listen. Okay. Let's say this point is 1, this point is 2. So this point is 1, this point is 2. So initially I'm assuming that this is a constant slope 0. It's a constant slope 0. Then at this point up to here, let me use another color. So from here to here you can see there is nothing change. Okay, this line is 0 line. Then at one point you are encountering a pole. So it means in this 0 line you are now adding a minus 20 decibel. So 0 plus minus 20 is nothing but a minus 20. So it will be a falling slope. That's why this resultant slope is minus 20. Then what is happening? So at this, from this point to this point, it is falling at the slope of minus 20. Then at minus 2 point or 2 point, you are encountering a 0. So initially you are going to minus 20. Now you are encountering a 0 means you are adding plus 20. So the resultant is again 0 decibel. So that's why it is 0 decibel. And now you got.
Yes, sir.
So these are all the related to Bode plots. Okay. And be, very strong in Bode plot. Okay. So similarly, you can see for a lead compensator. Okay, you can see that I'm starting with 0. Let's say I'm starting with 0 decibel per decade. Then you have to increase plus 20. Now you are increasing plus 20. Then again you are encountering a pole. So plus 20 and minus 20 they cancel. Again you have to go into 0 decibel. So you can see this is a completely high pass filter. It only allows high frequencies and blocking the low frequency component. So in that way you can try to understand that lag compensator is a low pass filter. Remember that lag is a 3-letter word, low is a 3-letter word. Lead compensator is a 4-letter word. It should be high pass filter which is having a 4-letter word. So like that way it is very easy. If you don't have much time to analyze. Just remember this way. Now I'm just going to the combination of all these three. Not only lag and lead is there, you have also the combination of lag and lead is there. Lag plus lead. Then which type of filter is this one? Can anybody tell me? Let me quickly draw it. Clearly I am saying this is a lag compensator. For lag compensator, you know that this is the zero and pole location. Then you are adding a lead compensator. You know that lead compensator is initially zero, then pole. So this is the overall pole location. If you just by yourself, if you want to draw the filter characteristics, what you do, you just give some location -1, -2, -3, -4. So these two now it's contributing a lag. Okay, these two is now contributing lead. So this is the lag lead. Don't go from here to here, always go from here to here, left to right, because okay, this is the way we are representing our poles. The pole should be always the left hand side of the S-plane. That's why lag and lead means always which one is close to origin, draw that one, then lead after that. Okay, if you draw the pole zero location, then how will get it? Initially how will get it? You will let me see.
Sir, if it is suppose lead plus lag,
You do this is the lead plus lag. So first you draw the lead. So your pole zero location will be initially you have a zero, then pole. These two will contribute lead, then lag. Lag means pole and zero. Okay. Now you
okay, sir.
do the what is I'm just trying to do. Which type of filter is this one? Lag and lead. Draw the body plot. Okay. Do the body plot of the system from here. Okay. So first of all you have a pole. Okay. So let me draw here the first one. Forget about lead lag, you can try by yourself. I'm just doing it for the lag lead compensator. So you have a pole at the origin. First you have to draw magnitude plot like that. So you are encountering a pole. Let's say you are starting with 0 decibel. Okay. Next, the slope is 0 decibel. Then what will happen? You are encountering a pole which is coming -20. Then you are again encountering a 0. 0 means -20 plus 20, again it will be 0 decibel. From 0 decibel again you are encountering a 0, means you are going again +20. Then again you are encountering a pole. So +20 -20, so it will be 0 decibel. So it will be structured like that. Okay. So if you what you do, if you clearly do this in mathematics, then what you will get it like this. So it is called a band stop filter, or it is called a notch filter. Okay, so lag rate compensator is a notch filter. Similarly, if you do for the lead lag compensator, how it will be? Lead and lag. Okay, this is a combination. This is lead, this is lag. Draw the body plot. So initially you are having a 0. Let's say I'm starting with 0 decibel here because I want to rise. So +20 I rise here. Then I have encountering a pole. So again you have a pole. Again you have to come back. Then you have to come back like that. 0, then again -20, 0. So it is clearly you can see a band pass filter. It is allowing the signal only within some range. Okay, this is the minimum range, and this is the maximum range. So this is the band pass filter. So like that way, the examinations you have to identify which type of filter is given to you. Okay.
Sir, why it is called notch filter previous lag plus lead?
Because it is having a notch here. Okay, it's at a particular frequency, it allows the cutoff. Okay, it doesn't
Okay,
allow any frequency, just having a notch. It's a notch shape like that.
Okay.
That's why it is called the notch filter. Next, how the question will be coming from this. Remember that if you give any questions to me based on this, I know this concept only, whatever I discussed, if I know all the concept, then I can clearly say. So let's say I'm just giving this example. This is a lead lag compensator, right? It is a lead lag compensator. Then what are the questions that will come in the examination? They will ask you to find out, okay, to find out the maximum frequency. Okay, so what is the maximum frequency of operation of this lead lag compensator? What is the maximum frequency? The maximum frequency is the frequency at which your gain should be equal to high or maximum. Gain is maximum at which frequency. You can clearly see that this region, okay, this region you are operating at a maximum gain. Okay, so you have to find out corresponding frequency at which the gain will be maximum. If I draw it actually, this is the actually Bode plot view. Actually the filter should be like that. Band pass filter is something like that, right? It is like that. So he is asking us at which frequency omega this uh, lead lag compensator gives a maximum gain. Okay, at this point you have to find out. So what is the omega? How to find out? If anybody know the Bode plot of the system, then you can clearly see that this is the Bode plot of the system. You have a two frequency. One, this is the one corner frequency. Okay, oh sorry, this is the one corner frequency or the slope is changing, and this is one corner frequency or the slope is changing. Corner frequency 1, and this is the corner frequency 2. So at these two corner frequency, okay, so what you do is just take the geometric mean of this these two corner frequencies. Let me give the first corner frequencies 1 by let's this time, in terms of time I'm giving. So this is, let's say, t1 and this is t2. Then what you do, you just find out the geometric mean of t1 t2. So this will gives you the frequency at which the gain will be maximum. Okay, so actually how it will be represented, the lag lead compensators, they are actually having a transfer function. Okay, because they are compensators, so it will be represented by only GCS. So it can be represented by 1 plus A into TS divided by 1 plus TS. This is actually the transfer function standard form of a lead lag compensator or a lag lead compensator. It can be lag lead or it can be lead lag. Okay, but it depends upon the value of A. Whether A is less than 1, then it will be a lag compensator. Sorry, A is greater than 1, it is a lag compensator. A is less than 1, it is a lead compensator. Okay, so now you can see you have a pole and clearly you have a 0. What is the pole location? 1 plus Ts equal to 0. So S equal to now minus 1 by T. S1 I'm writing, this is the pole. What is the 0 location? 1 plus ATS equal to 0. This is S is somewhere here. Okay, so now S equal to how much? Minus 1 by 80. So this is this 0 location. Now what do? You have to take the geometric mean of these two. Geometric mean means S1 and here is S2. Let's take the geometric mean of that. So minus 1 by T into minus 1 by AT. If you take the geometric mean, then it will be 1 by root over of A into T. This is the value of omega at which your gain will be maximum. Okay, so remember this formula. Okay, you can easily find out at which frequency your gain will be maximum. And after finding out that omega value, you put that omega value here in this equation to get the maximum gain, because initially you find out at which frequency it will be maximum, and corresponding frequency put in the original equation to gain the system gain, actual gain. Okay, what is the maximum gain? Okay, let me do one question, otherwise you'll not be able to understand. Okay. R1. One more slide. Okay, let me give an example. This is your input voltage, this is your output voltage, this one is given R1, you can take C1, and this is R2. Now tell me that whether this is a which type of compensator, okay, whether it is a lag compensator, lead compensator, lag lead compensator, or what the combination of these. Okay, so for this, what you need to find out, for any system like that it is given to you, first of all you have to find out the input voltage divided by, means what is the transfer function you need to find out, output voltage divided by input voltage. Okay, so what you do, take this R1 and C combination as Z1. Z1 is now R1 parallel with C1. Okay, so now simplify the circuit by impedance. Okay, this is an impedance, you can write down here, having Z1. Now here is R2 is given. Now this is your V0, this is your input voltage Vin. So now you just apply a voltage divider rule. What is the voltage across R2? It will be V0, which is nothing but R2 divided by R2 plus Z1 into input voltage. So V0 divided by V input voltage is nothing but your R2 divided by R2 plus Z1. Now what you do, you simplify this one, okay, and tell me the final answer. Otherwise, let me simplify for you. I'm writing here. I'm just giving an example like that. Try to understand. Let the transfer function I'm giving you, by I'm putting some value of R2 and R1 C1, I'm getting something like that. 1 plus 0.3 s divided by 1 plus 0.17 s. This is the transfer function you are getting, let's say, okay, and you have to compare the original transfer function in the previous slide I told you. This is the compensated transfer function is nothing but 1 plus a into ts divided by 1 plus ts. So now you compare with standard this equation. So a into t, I'm just writing different color. Here I'm writing, if you compare here in this to equation number 1 and equation number 2, what is the value of a and t you have to find out. So a into t is now 0.3 and t is now your 0.17. From here you can find out what is the value of a, 0.3 divided by 0.17. What is this value? This value is approximately 30 divided by 17. 30 divided by 17 is greater than 1. A is greater than 1. If a is greater than 1, it is a lag compensator. Okay. You understand? Okay. So after you finding out whether lag or lead compensator, you see the value of A is greater than 1, it is a lag compensator, A is less than 1, it is a lead compensator. Then what you need to find out, you have to find out for what value of omega, okay, this gives a maximum gain, this compensator is giving a maximum gain. So find out that this will be nothing but 1 divided by root A into T. Already find out from the previous slide, you can see this is maximum omega m equal to 1 by root A into T. Okay, so now if you put the value of T and A, you will get omega. So this is nothing called omega m, because I'm calling omega m is the maximum gain frequency at which your gain will be maximum. Okay, so in this way actually just need to touch this concept of lag lead compensator, lag compensator. Okay, I don't have much questions here right now with me. Okay, you can go by yourself and solve some numericals, okay, from different books, not only concentrate on only one books. You can see the previous questions, okay, and any numerical books you're following control system, okay, you can check it out, okay, and see how they are solving the questions of a lag lead compensator and how you are going to approach the questions. Okay, always try to solve in less minute, okay, less seconds, so that it will save your time. And okay, I have this much content for today. Okay, in the next class we'll have something.
Sir, I have one doubt.
Yeah, sure.
Sir, the steady state error to the unit ramp input without proportional derivative filter is ESS is equal to 2 zeta by omega n.
Sorry.
So steady state error is 2 zeta by omega n for the unit ramp input,
Okay.
and this is without proportional plus derivative filter.
Okay.
And it is asked find what is the value of k when the steady state error for tracking RAM input may be eliminated. Steady state error.
Okay, you are giving a ramp input. Okay.
Yes, yes. Unit RAM.
Okay, so remember that for a unit ramp input, your steady state error is always constant.
Yes, yes.
Okay, what is that value?
1 by kV.
1 by kV for a unit ramp input. Yeah, it's okay. The steady state error is okay. But what is your exact question? If you get, suppose, let some steady state error 1 by kV, then
When we introduce the proportional derivative filter,
okay.
then what will be the value of k when the steady state error may be reduced to zero?
Okay, let me solve here this question. Some space. Let me solve here. You are saying that you have a steady state error, which is
Sir,
1
it
by,
is a second order system is there.
yeah,
Okay. And input is means they introduce the proportional plus derivative filter 1 plus ks.
okay. This is, they're adding something,
1 plus ks.
1 plus ks, okay.
And they are saying that the steady state error to the unit ramp input
Hmm.
without this proportional plus derivative filter is zeta to zeta by omega n
2 zeta
by
by
omega n. This will be the steady state error without this controller.
compensator, right?
Yes, and now they are asking that they introduce this controller. Okay, then what will be the value of k when steady state error is zero?
You're adding this now to make this error equal to 0, right?
Yes, and they have given the option that is k is equal to zero, k is equal to 2 by zeta omega n, k is equal to 2 zeta by omega n, and k is equal to 2 zeta omega n.
Okay, something they are giving. Okay,
आज की sensations और
sorry, anyone is saying something? Okay, so what you do, if you have a closed loop transfer function, okay, and they have given already a steady state error is 2 zeta by omega n, to make that error equal to 0, you are adding a 1 plus k something, okay. Then how we are going to approach this question, what is the value of k, such that you are making your steady state error equal to 0.
Yes, sir.
This is the question. I understand what is the questions. Okay, let me try. Okay, second order system, we are giving you unit ramp input. This is the ramp signal. Solve which is steady state error, which is something is the time constant. Okay. So what you do to make this error equal to 0, you have to find out the time constant of the system. Time constant of the system is 1 divided by zeta omega n.
So I think, suppose, sir, when the steady state error is 0,
Right.
the k value should be 0, na?
Why the k value equal to 0? No, you are just because the steady state error is always they are giving. Okay, this 2
Yes,
zeta
sir.
by omega n they are giving. Okay, this 2 zeta by omega n. Now, actually, what is happening whenever you are applying a ramp input? What is there? This is the input. Okay, this is a ramp signal T. Okay, but output of your system is always like that. Okay, there is always exist a steady state error. Okay, whenever you are applying a ramp input, from the input to the output, always there is a steady state error, and that steady state error is your time constant. So whatever your time constant, they are giving that the time constant is now 2 by time constant is given 2 zeta by omega n. This is the steady state error. Okay, t equal to 2 zeta by omega n. They are giving to you. So now here they are adding this 1 plus ks term to make your steady state error equal to 0. Okay, so here they're adding some k 1 plus k into s to make the steady state error equal to 0. It means this 2 zeta by omega n they want to nullify. Okay, how to this nullify? So they're adding. Are you sure that they're adding this 1 plus ks term? In the question it is given 1 plus ks, right? Hello?
Yes, sir. 1 plus ks is a proportional plus derivative filter is introduced
Okay.
in the system to make the steady state error 0. So what will be the value of k?
Okay. Okay, what is your approach to solve this question? I understand a little bit. Anyone who's having any idea to how to solve this question?
Sir, if the error is 0, the output of control is 0 or some like that?
No, no, no. Error is 0. Output of the controller is not 0. Okay.
Okay.
Output of the controller some value. It is going to the plant. It cannot be 0. Output of any compensator is not 0. Input you have to make 0. Error you have to make 0. Not the output. If the output will be 0, then what is going to the controller? Controller will not take any action. It's not like that. Okay, I'll come to back. Just send me the question in WhatsApp. I'll solve it and I'll come back to you.
Actually, this is the question from the assignment, sir.
Oh, it's from the assignment.
Yes, yes.
Okay, try to solve by yourself from the
Okay,
assignment
okay.
question. Okay.
Thank you, sir. Thank you.
Okay. Okay. Just today for today, I'm stopping here. Okay. For
Thank you,
any
sir.
doubt, you can come and ask for my personal chats. Okay. So thank you all of you for joining the session. Okay.
Thank you very much, sir.